Okay, so today we're going to be talking about closed sets in a topology. So one thing when you're not, when you come into topology with no previous experience and you hear open and closed, you might want to assume that, they're sort of opposites and that a set can't be both open and closed, or a set either has to be open or closed. So first and foremost, those are both false, right? You can have sets that aren't open or closed, and you can have sets that are both open and closed. So I guess I just wanted to get that out of the way. So by definition, A is a closed set if the complement of A in the topological space X is open. So closed sets are just complements of open sets. So this allows us to say three things about closed sets. First is that the empty set and X are closed. Because the complement of the empty set is X, which is open, and the complement of X is the empty set, which is open. The next thing is that if you have a family of closed sets, then the intersection of this family is closed. So why is that, right? This follows immediately from De Morgan's laws, because we know that the union of a family of open sets is open, right? And if we take the complement of a union, we get an intersection of complements. So essentially, we would have X complement this intersection. So lambda over lambda is going to be a union of X lambda, and each of these sets is going to be open, and a arbitrary union of open sets is open. So this is open. So the complement of this intersection is open, so the intersection must be closed. Similarly, by De Morgan's laws, if A1 and A2 are closed, then A1 union A2 is closed. Because we have the opposite rule for open sets, that the intersection of two open sets is open. So now let's relate this notion of closed sets back to some of the things we talked about last time. So one of these things would be the boundary of a set. The boundary of a set is always closed, right? And let's see why that is. The complement of the boundary, as we said last time, the boundary interior and exterior form a partition. So if you take the complement of the boundary, you're going to get the interior and the exterior. But remember, the exterior is just the interior of the complement of A, and interiors are always open. So these are both open sets. So this is an open set because the union of two open sets is going to be open. So since the complement of a boundary is open, this shows that a boundary is closed. We also have a union a boundary is closed. And why is that? Well, last time we said that a union a boundary is equal to x minus a exterior, and a exterior is an open set, right? Because it's the interior of x minus a. So this is the complement of an open set. Is the let me move my tablet up a little bit. Is the complement of an open set. So it has to be closed by definition. And so this A union a boundary is what we are going to define as the closure of A, and we're going to denote it as A with a line over it. So this is called the closure. And this is a very important topological operation, more important than the interior, I would argue. Although they're sort of duals in a sense. We'll see that. So, of course, we've just shown that, of course, the closure is closed, right? That's something natural we would expect. There's a nice point characterization of the closure, which says that the points of the closure are exactly the points such that for any open set which contains P, right, this point, U intersect A does not equal the empty set. So what is this saying? First of all, this looks reminiscent of the definition of the boundary. The boundary had an extra statement which said that the intersection with the complement of A would also be non-empty. But we're not saying that now, right? That's sort of scratched out. Of course, if P was in the boundary, then this would in fact be true, right? Because U has to contain a point in A and x minus A. So of course it's going to contain a point in A. If P was in A, then of course U intersect A is not going to be empty because P is in U intersect A. So there we can see why that would prove the forward implication, right? Because for P to be an element of A closure, since we've defined it as a union, we would have to break it up into two cases, right? We break it up into a case of P being an element of A, in which case U intersect A is not empty because U intersect A contains P. And then, or we could do the case where P is contained in the boundary, in which case U intersect A is not empty by definition of the boundary, right? It may not be that P is in this set, but we know by definition of the boundary that this has to be non-empty. And then for the reverse implication, you essentially have to use the fact that the closure is the complement of the exterior, because if U is always intersecting A, then this means that no such U can be fully contained in the complement of A, right? Because the definition of A exterior is that if a point is in the exterior, then you can find a open set containing P, which is contained in the exterior. But since A and A exterior, since A and the complement of A are disjoint, right? You can't have a point in A and X minus A, then since you're always going to have a point in U contained in A, you can't have U fully contained in X minus A. And so this shows that this description is exactly a description of X minus A exterior, which is a closure. Moving on with more descriptions of the closure, we also remember with the interior, we said that the interior is the union of all open sets contained in A. Similarly, if we define a family, this is going to be a family of closed sets, and A is going to be contained in B sub lambda. So this is the family of closed sets which contain A. Then A closure is going to be the intersection of this family. So the closure of a set is the intersection of all the closed sets which contain A. And again, I think you can use yeah, you should be able to use De Morgan's laws, essentially by saying that this is equivalent to saying that A exterior is the union of X minus B sub lambda. X minus B sub lambda, these are going to be open, and since A is contained in B sub lambda, if we take negations, we would get the complement of B sub lambda is contained in the complement of X minus A, and of course A exterior right here is just X minus A interior. So this is something we've already proved. So these are equivalent by De Morgan's laws. So once you proved the interior formula, you can prove the closure formula. So now that we've defined the closure, we have some more nice characterizations for closed sets, right? A set is closed if and only if it equals its closure. And another equivalent thing is that A contains its boundary, right? Because since A closure is A union A boundary, if this is equal to A, then that means taking a union with a boundary does nothing to the set A, right? So that means that the boundary is contained in A. Of course, that's sort of hand-wavy, but you can prove that using a point set proof, right? Something that follows from this is that taking the closure of a closure is just equal to the closure because this is a closed set. Another useful thing, and we had a similar thing for the interior as well, is that if we have a set inclusion, A is a subset of B, then the closure of A is a subset of the closure of B. Rather nice. And then we have some rules for taking closures of unions. So these are less of rules and more of theorems, things you should prove. And so here again we had a similar thing with the interior. We get that we only have set inclusion for the second part, taking a closure of the intersection. So again, you should find an example where the closure of A intersect B is not equal to A closure intersect B closure, right? Or not, am I thinking? Yeah, where it's not equal to. And then the last thing is a definition of something that isn't it's not going to be useful for us now, but it is something that's used like later on, I'd say more in an analysis, and that is a dense set. So A is dense, means that the closure of A equals the whole topological space X, right? So for instance, X is a dense set because the closure of X is X, right? So yeah, that concludes this lecture. Do you have any questions?
No, I've got all.
You're good?
Yeah, I'm good. I got it.
All right. Well, that concludes this lecture.